Hello students, today we are going to discuss applications of dimensional analysis. In this series, today we will discuss the third applications, or we will learn it, because first two applications we have already discussed in our previous video. The third application of the dimensional analysis is to derive the physical relationship among various physical quantities. By the use of dimensional analysis, here we will derive the relation between various physical quantities. This is possible. We can derive this relation for the physical quantities by the use of principle of homogeneity. We will apply the principle of homogeneity of dimensions, and if the dimensions of the physical quantities are known, we will place the dimensions as per conditions given in the problems. Here we will take one problem, one example, by which we will explain how the physical relation among the various physical quantities can be derived. Here we see that problem is given in which we have to derive the relation. That problem is the kinetic energy possessed by a body depends upon its mass. Here the dependency of kinetic energy is on the mass of the body. So first we will write kinetic energy. We can give symbol to it, E. This E is directly proportional to mass. So symbol for the mass is given A, and we don't know if this energy depends upon mass in which form. Either depends linearly, or depends in second power, or depends in inversely. So we will place here dimension of M is A. Secondly, it is given the same kinetic energy depends upon speed. So we will write here V raised to power B. On combining these two, E proportional to M raised to power A, V raised to power B, or E equal to K M raised to power A, V raised to power B. Here K is the constant of proportionality. It is one of the dimensionless constant. It is a constant of proportionality, and it is one of the dimensionless constant. Now we will place dimensional formula for E, that of mass and that of velocity also. Place the dimensional formulas here. Dimensional formula of kinetic energy. Kinetic energy is a kind of energy. Sorry. It is mL2 T minus 2. Energy having the dimensions of work equal to K mass. Mass having dimension 1 raised to power A. Velocity LT minus 1 raised to power B. On simplification, this becomes M raised to power A, L raised to power B, and T raised to power minus B. Now comparing the dimensions of M, L and T on both sides. When you compare the dimensions, in left hand side dimension of mass is 1. Here dimension of mass is A. So 1 equal to A. Dimension of length here is 2. Dimension of length is here 2. So here is B. So 2 is equal to B. And it is also B. Again B is there. So minus 2 also equal to minus B. Minus cancel with minus. Again B equal to 2. Here we see that we obtained value of A is 1 and value of B is 2. So place the value of A and B in equation 1. When we place the value E equal to K in place of M, it is M raised to power 1. V raised to power 2. So E equal to K M V square. This is the relation which is obtained by the principle of homogeneity and by the use of the dimensional analysis. This is equation number 2, which is the required relation. Now take one more example. Derive by methods of dimensions an expression for the time period t of oscillation of simple pendulum. Here we are assuming this time period of the simple pendulum depends upon length of the pendulum, mass of the bob of the pendulum, as well as acceleration due to gravity. In this problem, we have to use methods of dimension and to find time period expression for the pendulum. Dependency is given here. The time period t depends upon first length of the pendulum. Symbol for the length is given here, so L raised to power A. Depends upon mass of the bob, so it is M raised to power B. Depends upon acceleration due to gravity. On combining these three, we obtain T proportionate to L raised to power A, M raised to power B, and G raised to power C. Or T equal to K, L raised to power A, M raised to power B, and G raised to power C. K again, a dimensionless constant. Now we will place dimensional formula of T, time period, in left hand side, length, mass and acceleration due to gravity on right hand side. In left hand side, it becomes M0, L0, T1. On right hand side, K is unitless, dimensionless. It is L1 raised to power A. It is M. B, acceleration due to gravity, L E minus 2 raised to power C. On simplifications of exponents, this becomes M raised to B, L, A is here, C is here, so L raised to power A plus C, and T raised to power minus 2C. T raised to power minus 2C. When we further simplify it, this is our equation number 1. On comparing the powers of M, L and T on both sides, we obtained here in left hand side power of mass is 0. So 0 equal to B. The value of B is 0. In the second expression here, power of L is 0, here power of L is A plus C. So A plus C equal to 0. And finally, dimension of time on left hand side is 1, on that side is minus 2C. Minus 2C equal to 1. So C equal to minus 1 upon 2. Place value of C here. So we will obtain A minus 1 upon 2 equal to 0. So A equal to 1 upon 2. Now we are having A equal to 1 upon 2, B equal to 0 and C equal to minus 1 upon 2. On placing the values of A, B and C in equation 1, we obtained T equal to K L raised to power 1 upon 2, M raised to power 0 and G raised to power minus 1 upon 2. Here we see that as time period of a simple pendulum does not depend upon mass. In the problem it was given time period depends upon mass, but in result we obtain power of mass is 0. Any number raised to power 0 is 1. So T equal to K L raised to 1 by 2 G raised to 1 by 2 with negative sign. So dependency of masses disappear. So the relation becomes K equal to root L by G, which is the required expression for the time period of a simple pendulum. In this manner, we can apply third applications of the dimensional analysis, that to drive the physical relation by the use of the dimensional equation and principle of homogeneity. At last, we will discuss here about limitations or shortcomings of dimensional analysis. These are the shortcomings or they are the limitations of dimensional analysis. There are 4 or 5 which we will discuss here one by one. First, limitations of the dimensional analysis is dimensional constant involved in physical relations cannot be determined. While we are driving physical relations and we are placing K is a constant of proportionality, and every time it may be a numeral or it may be other dimensionless quantity. That dimensionless quantity cannot be determined by the dimensional analysis. Like as the time period of a simple pendulum T equal to 2 pi root L by G. We are unable to find K's value 2 pi by this relation. So this is the first limitation of dimensional analysis. Second, dimensional analysis method unable to drive the relation having addition and subtraction sign. This analysis is only used to drive the relation having multiplication and division sign. Like 3 equations of motion, V equal to U plus AT, S equal to ut plus half at square and v square equal to u square plus 2as cannot be derived by the methods of dimensions. So this is the second limitation of the dimensional analysis. The physical relation carrying the positive and negative signs cannot be derived. Third, this dimensional analysis is failed to give information about trigonometric functions, logarithmic functions, exponential functions and other complex quantities involved in the physical relations. About those relations cannot be derived by the use of the dimensional analysis. Fourth, dimensional analysis failed to derive the relation involving more than 3 quantities. There are some physical relations which are used in physics carrying 4 or 5 quantities, but the relation for those quantities cannot be derived by the methods of dimensional analysis. This is one of the important limitations of the dimensional analysis. Only relation involves mass, length and times. those relations can be derived by the methods of dimensional analysis, and expression involving current, temperature, or amount of substance or luminous intensity, those relations cannot be derived by the methods of the dimensional analysis. Last but not least, a dimensionally correct relation may not be a true relation. A physical relation may be given to us which is dimensionally correct, but it is not 100% correct. Like a relation nu equal to 1 upon 2 root f by m is a physical relation which is correct 100% dimensionally. Dimensions of left hand sides are same as the dimensions of right hand side, but this is not the correct formula. The correct formula for the expression is nu equal to 1 upon 2l root f by m. Okay, this is the correct formula. This is the formula which is dimensionally correct, but this is the correct mathematical formula. So, above mentioned few are the limitation. That's why this dimensional analysis is not widely used for the derivations to derive the physical relations by the use of dimensional analysis. Okay, this is all about applications of dimensional analysis and limitations of dimensional analysis. Thank you so much. Thank you.